Problem 1. Estimate the energy required to raise the temperature of 2 kg of the following materials from 20 to 100 degrees centigrade: aluminium, steel, soda lime, glass, and high density polyethylene. So we know this data we have been given over here. So this is the data for the specific heat. So we have this data for the specific heat, which is the energy needed for 1 kilogram of the material to raise its temperature by 1 degree centigrade or 1 degree Kelvin. So in the case of aluminium, this specific heat is 900. So 900, and the weight is 2 kilogram. Weight is 2 kilogram, and temperature increases from 20 to 100 degrees centigrade. So centigrade and Kelvin are same in magnitude, so it should be 100 minus 20. So it will be the value will be, I think it should be 1.44 into 10 to the power 5 joules. So similarly for steel, it will be 486 into 2 into 100 minus 20, and then we can get the value. So therefore these will be the amounts of heat in joules. So in terms of kilojoules, so it should be 700 and no, it should be 77.76 kilojoule, and it will be 134.4 kilojoule, and it will be 296 kilojoule. Problem 2. Determine the room temperature heat capacities in joule per mole Kelvin at constant pressure for the following materials: aluminium, silver, tungsten, and 70 copper, 30 zinc, brass. How do these values compare with one another? How do you explain this? So for aluminium, for example, the specific heat value is 900. So it is 900 joules per kilogram Kelvin. So 900 joule per kilogram Kelvin means it is 0.9 joule per gram Kelvin. Okay, so for 1 gram, that means for 1 gram it is 0.9 joule. It means that for 1 gram mass, the specific heat is 0.9 joule. So for 26.98 gram mass, the energy will be 0.9 times 26.98, which is equal to 24.28 joule. So since 26.98 gram aluminium is 1 mole, okay, so therefore its unit will be like 24.28 joule per mole Kelvin. Okay. So similarly for silver, it is 235. So divided by 1000 by the same method, multiply by its atomic weight 107.87. So it will be 107.87 into 0.235. So it is 25.35. So it will be 25.35 joule per mole Kelvin. And similarly for tungsten, okay, for tungsten maybe we can do it here. It is 138 times 183.84, 138 per 1000, and then so it is 25.37. 25.37. Okay, so for 70 copper, 30 zinc, we need to find its average atomic weight. So average atomic weight will be 0.7 times 63.55 plus 30 times 65.41. So 0.7 times 63.55 plus 30 plus 0.3 times 65.41, which is equal to so actually it is should be 0.3. This average atomic weight will be 64.01, 64.11, and its specific heat will be then 375 divided by 1000 into 64.11. So 24.04. So as you can see that joule per mole Kelvin, as you can see that all these four values are very much near to each other. This value, this value, and this value, and these values are almost equal to 3 times the gas constant. 3 times 8.31 is equal to 3924.93, okay, joule per mole Kelvin. So this is due to the reason because all the these four metals all these four metals are at the room temperature, and there is a temperature which is called as the Debye temperature. So and their Debye temperature is much lower than the room temperature. Okay, so since they are in current state, they are much higher than their Debye temperature, so their specific heat value in terms of the mole are much closer to each other, almost the same. So here is the explanation. So these values of Cp, that means the specific heat that is the heat capacity at constant pressure, are very close to one another, because room temperature is considerably above the Debye temperature for these metals. So therefore the values of Cp should be about equal to 3R, which is indeed the case for all four of these metals. Problem 3. For aluminium, the heat capacity at constant volume Cv at 30 Kelvin is 0.81 joule per mole Kelvin, and the Debye temperature is 375 Kelvin. Estimate the specific heat at the following temperature. Okay, so remember that for the specific heat we normally use the units. Joule per kilogram Kelvin. Okay, so in this case we have this equation. This is the equation for the heat capacity related with the temperature. So and A is the proportionality constant. So heat capacity given is 0.81 joule per mole Kelvin. A will be then found as A, and the temperature is 30 Kelvin. 30. So from here the value of A will be 0.00003 joule per mole K power 4. Okay, and then this value of Ka can be now used. So now it has been asked that if the temperature is 50 Kelvin. Okay, so 50 Kelvin is above the Debye temperature. 50 Kelvin is no, below the Debye temperature. Okay, so we can use this equation. Okay, this equation is applicable when the given temperature is less than the Debye temperature. Okay, so it is 0.00003 multiplied by 50 Kelvin, so the power 3, so it will be 3.75 joule per mole Kelvin. So we need to convert this value into the joule per kilogram Kelvin. So we know that for aluminium 1 mole is equal to 26.98 gram. Okay, so it means that it will be 3.75 joule per 26.98 gram Kelvin, or in terms of kilogram Kelvin it will be 3.75 multiplied by 1000 divided by 26.98 joule per kilogram Kelvin. So as we calculate, this value will be 139 joule per kilogram Kelvin. So this will be the specific heat at constant volume at 50 Kelvin. For this value 425 Kelvin is higher than the Debye temperature, which is represented by theta. Okay, so since it is higher than the Debye temperature, so specific heat at constant volume at this temperature 425 Kelvin will be equal to approximately equal to 3 times the gas constant. 3 times the gas constant is 3 times 8.31, and then that will be in joule per mole, so it will be then 24.93, and then if similarly we can divide it by 26.98 and multiply by 1000, so we will get an answer which is equal to 923 joule per kilogram Kelvin.